So from the previous class, we know that when light falls on a photopigment, there is a change in the photopigment and a conformational change, and it activates uh, phosphodiesterase eventually, and then the phosphodiesterase breaks down cyclic GMP, and thereby the absence of cyclic GMP closes down the cyclic GMP gated non-cationic channel. So this is what we know from the previous class. Now let's see what the second messenger system does. It amplifies. So the second messenger system is for amplification, whereby even one photon. This is more particularly true in the case of rods, where even one photon will bring about hundreds of transducins being activated, and then hundreds of transducin will activate thousands of phosphodiesterase, and then phosphodiesterase will hydrolyze cyclic guanosine monophosphates, and the absence of cyclic guanosine monophosphates will close the gated channels, and cations will not enter. So hundreds of channels will be closed by the floating second messenger cyclic GMP in the cytoplasm, and then influx of huge amount of sodium ion will be blocked, also calcium ion will be blocked, and thereby hyperpolarization of the photoreceptors, which will be as high as 1 millivolt, and thereby stopping or retarding or lessening the flow of the neurotransmitter glutamate from the axonal end of the photoreceptor, thereby signaling downstream. Now, in the previous chapter, we have seen how a small amount of light, even one photon, brings about a hyperpolarization of the photoreceptors. So we must immediately end that signal, and we must promote the return of the photoreceptor to the dark state, whereby it is readied again to receive more light. So what happens is that the light excited photopigments are phosphorylated, and they will become unable to activate transducin. So the photopigments are broken down. And the bond between the retinal and opsin, this is the protein part. This is the chromophore, and they will be broken down, and the photopigment or the opsin part which remains behind is known as bleached, or rather the whole of the photoreceptor is bleached, and the regeneration occurs in the dark. We need darkness for that, and this is a part of the scheme of dark adaptation, whereby the 11-cis retinol, which has changed to all trans retinol, will be taken up by the pigment epithelia, and in the presence of vitamin A will be converted back into 11-cis retinol and will attach with opsin to become a ready photopigment again. So, and also moreover, transducin will have intrinsic GTPase properties. So the GTP which is attached to it is broken down, and it cannot stimulate the guanylate cyclase anymore. So the cascade is broken down, and the photoreceptor is again ready for another volley of light. Now, regarding dark adaptation, so we talked about dark adaptation. It means that suppose a person walks into a darkened area, suppose into a film theater. So the first thing you see in a film theater, you will be able to see is the screen, because there's some amount of light. But the seating arrangement, the aisle, and the alleyway for walking will not be visible immediately. So you will be kind of blind, because the rods which have already been bleached in the external sunlight will have to regenerate the photopigment, and this takes time. This will take 15-20 minutes. After 15-20 minutes, things will come back to normal, and you will have a adequate sight even in the dark. Now, for person who by virtue of their profession have to shift from a lit area to a dark area, from a dark area to a lit area, back and forth, and they also have to work in the dark. They cannot wait for a very long period of time to start working. So what do? They use red goggles. People like radiologists who work in the dark, X-ray, CT scan, things like that. Photographers in the dark room. Then pilots and air traffic controllers. So they use red goggles because rods, which provides you most of the enhanced dark vision, is not sensitive much to red light. So the red goggles, the use of red goggles will not bleach the rods even in a brightly lit area. So a person can wear a red goggles and go to the brightly lit area, go to the sunlight and come back and start working almost immediately. So that the rods, individuals, the person's rod are not bleached and vision in low lit area remains good. Okay, so this is why red goggles is used to accelerate dark adaptation. Now, what is light adaptation? See, dark adaptation was more sensitivity in low light, more sensitivity of vision in low light. Light adaptation is less sensitivity in bright light. So the situation is reversed. So if you walk out from a darkened theater after a movie and you walk into the sunlight, you will be immediately blinded. There will be so intense volume of light, you will have to close your eye or you will have to squint. And then gradually, you will be able to open your eye and resume normal vision. What happens is that the rods are immediately bleached and the cones take a little more time to, because that bright light vision is cone vision, that is what remains intact. So what happens is that when the person was in the dark, there was a entry of calcium and sodium and the photoreceptor, as you know, was depolarized. Now the entry of calcium does three things. So it enhances the photopigment phosphorylation, it retards the guanylyl cyclase, which also retards the manufacturing of the cyclic GMP. It also retards the opening of the, it directly retards the opening of the non-specific cationic channel. So in the dark, the tendency is for the photoreceptor to be depolarized. Although it is being any amount of light will hyperpolarize it, the tendency is to depolarize by closure. But what happens is that in the presence of light, this gate will close, and calcium will not be around. So let us see what happens. When calcium is not around, this phosphorylation will stop. This inhibition of cyclic GMP, the inhibition of manufacture of cyclic GMP by guanylyl cyclase will stop, and also the direct inhibition of the opening of the gate will stop. So light adaptation, that is when the person walks into a brightly lit area from a dark room, happens faster than dark adaptation. What happens is that the activity of guanylyl cyclase is accelerated, more cyclic GMP is manufactured, thereby opening the gate. The gate directly also is not inhibited from opening, it opens more easily, and the photopigment phosphorylation is hampered. So we get more intact photopigment, thereby some amount of depolarization is possible even in direct sunlight, so that some amount of vision can be retained. So we'll have to study a little bit about rods and cones. Cones, as you can see, are relatively thinner and they're tapered. Rods look like rods. What do they do? Rods. So rods have what is called, they help in scotopic vision, that is dim light vision. That is, rods will be able to give you some idea of luminance and some amount of useful vision even in moonlight and starlight. So it is 1,000 times more sensitive to light than cones. But being more sensitive, it loses out on accuracy. So it cannot localize very nicely, it cannot demarcate or differentiate very well between edges in low light. So it's because of a few factors. One of the factors being that majority of the rods, in fact, rods are not found in the central location of the retina. All the rods are found in the peripheral retina, and the focus of the external light by the various refracting media of the eye is very poor or distorted in the peripheral retina. So that's one of the reasons. localization is poor or accuracy is not very high. Whereas accuracy at the fovea, the central portion of the eye is very high because the image is highly conserved. It is a very good image, and all the media like the cornea, the lens will provide the highest amount of uh, accurate focus on the fovea. The second reason why the accuracy is low is because many rods will converge on a bipolar cell. So the area from which light is collected is large. The area of collection of light is large. But because it's so large an area, the localization or the specificity of where a photon struck is very poor. So you have low accuracy but very high sensitivity to light from rods. Cone, on the other hand, will give you daylight vision or bright light vision. They are very accurate. So what does cone do? Cone does three things: A, B, and C. A is acuity of vision, or vision is very accurate when light falls on the cone, because cones are concentrated in the fovea and the focus on the fovea from the eye is also very good. Then B, cones will only be active in bright light, and cones are responsible for color vision. As we know, we have three types of cone with three types of photoreceptors. So red photoreceptor containing cone, the absorption is at around 560 nanometers. This is known the L-type cones. Okay. Then we have the M-type cone, which detects green, and the maximum sensitivity is at 540 nanometers. And then we have S-type or small type cones, where the maximum absorption is at the blue spectra. It is around 430 nanometers. Now, this L-type cone or the red and the M-type cone green are the two types of cones which are found in the fovea. So only L-type and M-type cones are found in the fovea, in the center of the focus of the eye, and they are concentrated to a great extent. They are thin, as you have seen in the picture, in the microscopic picture. They are thin and they are concentrated in the fovea, so that they give acute vision, or the vision from fovea is very accurate, and they also provide color vision. Now, S-type cones are not found in the fovea. They are found a little away from the fovea in the peripheral retina, and they are very less in number. We also have the presence of a fourth photopigment, which differentiates between light and dark, and it is not perceived in our consciousness. And interestingly, this photopigment is found in ganglion cells, which will project to the hypothalamus. And what does it do? It synchronizes the circadian rhythm, the rhythm of 24 hours, day and night, dark and light. Okay? And also it synchronizes long-term rhythms like monthly rhythm, yearly rhythm, and even longer. Okay, so melanopsin found in the ganglion cells. There is also a term known as the Purkinje shift. Now, what is the Purkinje shift? So we talked about photopic vision, we talked about scotopic vision. So photopic vision is daylight vision, scotopic vision is dim light vision. Now, what happens in between? Suppose we have a period of the day, or we have a area in the room which has neither very high illumination like in the day, or it's not absolutely dark. It's somewhere in between, like in the dusk, the period where sun has gone down. So that period has a special effect. So what do we have is that during that period, rods are able to gather some amount of light, and they will boost the cones. So rods will get some amount of light. They will be hyperpolarized, and this signal downstream goes to the cones and is goes through electrical synapses. So there is almost no delay, there is almost no decay to give color perception. So at dusk, we may be able to perceive some color. It is not like absolutely dark, as in the moonlit night or starlit night, where we don't see any color. We only see shades of gray. It's black and shades of gray. So during mesopic vision, we can see some color. But what happens is that gradually red fades fast. Now let's take an example. Suppose we have a rose bush and we have red rose on that bush. So initially in mesopic vision, the red roses will start to darken and they will become gray and black. And then after that, the green leaves will become gray and black. And then it will be all black. So this transition from daylight vision to dim light vision, the transition, the mid portion is the mesopic vision, where this unique thing happens. The rods will boost or enhance the ability of the cones to perceive light, whereby red will fade first and green will fade last. Okay, this is Purkinje shift, the shift from photopic vision to scotopic vision, whereby you see the colors fading in this progression. Now, let's start talking about bipolar cells. What do bipolar cells do? So bipolar cells will connect photoreceptors to ganglion cells, which will form the optic nerve. So photoreceptors, bipolar cells, ganglion cells, optic nerve to the brain. Now it has been seen that photoreceptors will be stimulated best or will respond best when they have a center stimulation, and the surrounding darkness. So here, this example has light in the middle and a dark surrounding. Now what happens is that when you have stimulation of light, this cell will be hyperpolarized. So light hyperpolarizes the photoreceptors. Now the interesting thing about bipolar cell is that we have two varieties of bipolar cell. The on variety and the off variety. This is the on variety, this is the off variety. So the on variety, how does it respond? How does it respond to light falling on the photoreceptor? Light falling on the photoreceptor will hyperpolarize the photoreceptor. Thereby, glutamate transmitter will be less. Now, please remember, this is very important. This portion is very. This is a very unique receptor area. This receptor area is a receptor where glutamate is inhibitory. Please note, this receptor area, glutamate is inhibitory. We have receptors here. These receptors are metabotropic glutamate receptors. These receptors are metabotropic glutamate receptors. As you are well aware, there are two kinds of receptor, metabotropic and ionic receptors. This is a metabotropic receptor. So, in the presence of glutamate, the metabotropic receptors will hyperpolarize this cell. In the presence of glutamate, metabotropic receptor will hyperpolarize the cell. Hyperpolarized cell will not release neurotransmitter, which is also glutamate in this case. So receptor receives light, receptor becomes hyperpolarized, doesn't release much glutamate, thereby this cell becomes depolarized. In the presence of light, this cell becomes hyperpolarized, doesn't release neurotransmitter. The lack of neurotransmitter depolarizes the cell. Because metabotropic glutamate receptors are hyperpolarizing in the presence of glutamate. So light will depolarize, and depolarization causes release of glutamate, and this glutamate will act on ionotropic receptors, and the ganglion cell will also be depolarized. So this pathway, photoreceptor, then depolarized bipolar cell, depolarized ganglion cell is the on pathway. This is the on pathway. Now see the other pathway. This photoreceptor is giving signal to both on and off pathway. This is a on bipolar cell. This is the off bipolar cell. Now what happens in off bipolar cell? In off bipolar cell, the receptor is different. You see, this is a metabotropic receptor. This is an ionic receptor. Here, when the cell is receiving light, it is being hyperpolarized. So a photoreceptor is hyperpolarized when light falls on it. When light falls on a photoreceptor, as we see in the center, it is hyperpolarized, thereby releasing less glutamate. A release of less glutamate will hyperpolarize this cell. Because in the dark, this was depolarized, this released a lot of glutamate. Glutamate depolarized this cell. So in the dark, the off-center bipolar cell is depolarized. But in the light, the off-center bipolar cell is hyperpolarized, or it becomes off. It doesn't release any neurotransmitter downstream. So this neurotransmitter is not released. In the presence of light, this neurotransmitter is not released, and then this neurotransmitter is not released. This whole pathway becomes less active. So in the presence of light, this pathway becomes activated. This is the on pathway. In the presence of light, this pathway is inactivated. This is the off pathway. So you see, presence of light here gives not one kind of signal, but two kinds of signal. A signal which is going through this ganglion cell. Obviously, in the ganglion cell, this will be action potential. Up till here, it is graded potential, release of neurotransmitter, graded potential, release of neurotransmitter. From here onward, it is action potential. So action potential will arise from on pathway that comprises of on-center bipolar cells and on-center ganglion cells in the presence of light. And in the presence of light, the other pathway will be deactivated and there will be no action potential. So you see, the presence of light gives to not one kind of signal, as is the case in other photoreceptor pathway, but here two kind of signals, on and off. Okay. So let's recapitulate. The off pathway bipolar cell depolarizes. So we're talking about bipolar cells. So what kind of bipolar cells? There are two kinds of bipolar cells, on and off. So the bipolar cell in the off pathway will depolarize when glutamate binds, or it so it generates AP in the dark. So it generates action potential in the dark. As we have seen in the previous example, it will not generate action potential in the light. So off pathways will only generate action potential in the dark, and they will turn off in light. Okay, so that is why it is off. So during the presence of light in their respective photoreceptor, off bipolar cell will not generate AP. But when light is turned off, they will generate AP. The reverse is the case in off pathway bipolar cell. On pathway bipolar cell depolarizes with lack of glutamate. Fine. So when do you have lack of glutamate? When the photoreceptor perceives light. When the photoreceptor perceives light, the bipolar cell has lack of glutamate and it depolarizes, thereby activating itself. Depolarization of a neuronal cell is activity increased in a neuronal cell and release of more neurotransmitter in its external terminal. So metabotropic receptors are present and cyclic GMP gated non-selective cationic channels will open. So this is something which we can discuss later on. So how does this help? How does these signaling, how does the ability of two bipolar cell downstream to photoreceptors help? They will increase the ability. What does it do? It increases the ability to perceive contrast at the edge or border. So if the edge or border between light and dark, between one kind of color to the other kind of color, because what we have seen in the previous slide is also applicable to cones and also applicable to rods. They are applicable to cones of all varieties, 3 varieties. So the edge at the border, the difference in color will all improve the image resolution. Okay, so this is one way in which image resolution is improved even inside the retina. Okay, so there is processing happening even at the level of the bipolar cells. So photoreceptor first cell of reception of light, the bipolar cell, and even within the bipolar cell we have two varieties, the on type and the off type bipolar cells, which will contribute to the on pathway or to the off pathway, and thereby increasing the contrast at edge and border and thereby improving image resolution. So what do we want to see next? We want to see also the contribution of lateral inhibition. So on top of having on pathway and off pathway, which is already signaling, separately the presence of a lit area from the presence of unlit area. In other words, defining the border between light and darkness, or defining the border between a given specific color to that of another specific color. We also have at this corneal level a thing called the lateral inhibition, whereby the cells which are neighboring each other will have influence on their neighbors. So neighboring cells will be influencing each other. How do they do it? Let's see. So we have a photoreceptor in the middle, which is in the presence of light, and 2 photoreceptors surrounding, which are in the presence of dark. So what do you expect? These photoreceptor in the presence of light will be hyperpolarized. These photoreceptor in the dark will be depolarized. So they will act differently. And in the middle, we have only now a on-center bipolar cell, which has metabotropic receptors. And in the presence of darkness, this is usually hyperpolarized. Okay. So let us see what happens. First and foremost, when we have the presence of light and the surrounding darkness, we have glutamate coming out of this cell. Now, glutamate is acting as an excitatory neurotransmitter here. Glutamate is excitatory here. Glutamate is inhibitory here, but it is excitatory here. So, excitatory glutamate will excite the horizontal cells, and you can see, so the horizontal cells are excited, but horizontal cells output is inhibitory. This cell is depolarized. It excites the horizontal cell, but the horizontal cell output, 2 cells, even the cell which has excited it, is inhibitory. Inhibitory, and the neurotransmitter is GABA. Fine. So what happens is that, see, this is also doing the same thing. This is also via the horizontal cell is inhibiting. This is also inhibiting. What is inhibition? Inhibition is increased hyperpolarization. Inhibition is increased hyperpolarization. So in the presence of light, this cell is already hyperpolarized, and the neighboring cells are adding on to the hyperpolarization, thereby decreasing the glutamate discharge from this cell to a very great extent. So what happens is that, so we have increased hyperpolarization of the photoreceptor in the middle. So the photoreceptor which is getting light is getting much more hyperpolarized than it alone could have attained. So with the help of its neighbor, it is getting much more hyperpolarized. So there is much more lack of glutamate released. This lack of glutamate will increase the on-center bipolar cell depolarization. So these bipolar cell will be depolarized to a great extent. Its activity will increase, its neurotransmitter amount will increase, and therefore increased depolarization of the on-center bipolar cell or the on-pathway bipolar cell, and thereby the on-center ganglion cell. So you see, the presence of light in the middle surrounded by darkness will only increase the signal. The action potential here will be greatly increased because there is a neighbor, there are surrounding neighbors who are experiencing darkness, and they have increased the hyperpolarization of photoreceptors. This is another way in which the contrast is increased to a great deal. Okay, so I think this is enough for today. Next we will study regarding the bipolar cell and also the ganglion cells and how they exit from the retina and go to the brain and much more. Thank you.